This conference will now be recorded.
So, good evening, everyone. So, today we'll learn about the variation of acceleration due to gravity. We have already learned what is acceleration due to gravity. That is, if we throw any object or we observe any free fall of any object, we see the acceleration due to gravity becomes g. Okay, and it is always acting towards the center of the earth. So this we have already learned. So in the calculation of acceleration due to gravity, what we have considered? We have considered the earth to be a sphere made of a concentric spherical cells. So that is the concept. This is called cell concept or concentric spherical cell concept. And the smallest one, the smallest cell is at the center and the largest cell is at the surface of the sphere. So as you can see, this is one cell having certain radius c. Okay, so this is another cell, even this is another cell. So these are one cell having different radius, and all the concentric cell altogether makes this sphere, which we are considering as earth. So by considering this concentric cell concept, if we calculate acceleration due to gravity at any point p outside, which is outside, so this in this case we are seeing acceleration due to gravity outside the earth or the sphere. So in that case, you look, the mass of this sphere will be concentrated, as if concentrated at the center. Okay, so that is what we had already discussed. But when due to according to this cell theory, when we consider a point which is inside the sphere, look, if this is at d depth, like if some point p is inside the earth, which is at small earth distance away, okay, and from the surface of the earth it is d depth. So according to cell theorem, this object small m will not be attracted by, will not experience attraction attraction due to the cell of radius, or sorry, thickness, cell of thickness thickness small d. So I mean to say this cell, this part will not exert any attractive force on this particular mass. So in that case, you have to consider the earth to be a sphere of radius. If the original radius is capital R or RE, so you have to take or consider the earth to be a sphere of radius this much, or a sphere of radius RE minus D. So this cell will exert an attractive force on this particular mass, like at this inside point. Okay, so with this concept we had actually derived the acceleration due to gravity on the earth's surface. So at this case I just want to mention one point here is that when we consider any point inside, the whole mass of the earth, if we consider the whole mass of the earth to be capital M, the whole mass of the earth is not going to be considered over here. So in this case, so gravitational acceleration, sorry, gravitational force experienced by this particular body, this body at P, will be g m prime small m by r e minus d whole square. Okay, and if I say, yeah, so in this case m prime, capital M prime is the mass of the earth having radius this much. Okay, re minus d. So in that case, you know, your m prime has to be calculated, and for that you need to know the density of the earth. If we consider the density of the earth to be uniform and it has a value rho, then we have to replace this m prime with this m prime will be equal to 4 by 3 pi re minus d whole cube into rho. If rho is the uniform density, mass density of the earth. So in that case, if we do that, then we will be able to find out the gravitational acceleration at that inside point. Okay, so anyway, we had already learned that at any point on the earth's surface, the gravitational acceleration, so we had learned already, gravitational acceleration at any point on the earth's surface or on the surface of the earth is given by g is equal to small g is equal to capital G gravitational universal gravitational constant into the mass of the earth, gm by r square. R square is the, r is the, here in this case let us say re, the radius of the earth. Okay, so this is the gravitational acceleration or acceleration due to gravity on the earth's surface. Now we have to see what is the, like how this acceleration due to gravity varies with latitude, sorry, altitude or the height or depth, and also we'll see with the latitude also, obviously we'll see due to rotation. So there are three factors. There are three factors with which g vary. So one is height, another one is depth, and due to rotation of the earth also, the acceleration due to gravity changes. At various latitude, we'll see various values of g. So those like these three things we'll see how g varies with height. We'll derive the expression for that, and we'll take up few examples also, and how g or acceleration due to gravity varies with depth, and how it varies due to rotation of the earth at various latitude. So first let us see how acceleration due to gravity varies with altitude or height. So first of all, we need to know for this. See, will be always consider the earth. Will consider the earth to be a solid sphere, solid sphere of radius r and mass capital M. So this is the assumption we have to always remember. This is the assumption that we are considering the earth to be a solid sphere of radius capital R, and it has a mass of capital M, and its center is at O. Center of the earth is at O. Now acceleration due to gravity at the earth surface, or at the surface of earth, we had just written that earth is g is equal to gm by r square. Let us write this equation to be 1. Okay. Now look, when we keep one object over here, the acceleration due to gravity is g. So now we have taken the object of mass m at here at h height from the earth surface. From the earth surface, it is kept at h height. So what is the distance of this particular mass, small mass, from the center of the earth? That is r plus h. So why, you might be thinking, why should we consider the distance between, see the gravitational force will be this one, gmm by r square, and these are, if you take two spheres, so always the distance will be measured from the centers. Okay, always distance would be measured from the center to center distances are. So this is what we have to follow here also. So look here, in this case also, in the equation 1, when we have taken this, written this g, like acceleration due to gravity, this distance capital R is actually the radius that is measured from the center. So if we just follow this equation only, then what we can write for this, let us write this as gh, the acceleration due to gravity at this particular height, small h, can be written similar way, r plus h whole square. If I write this as equation 2, now what we'll do, we'll just take ratio of this equation 1 and 2. So I am just dividing what I am writing. I am dividing equation 1, sorry, 2 with equation of 1. So if I do this operation, look, I'll maybe, okay, I don't have space in the next slide. So what I'll do, I'll just remove, or maybe I'll write these equations side by side in small font. So G is equal to Gm by R square. This is equation number 1, and equation number 2 is this one, Gm by R plus H whole square. This is at any height at this particular place. G is Gh at this particular height on the surface. The acceleration due to gravity is G. Now what I'm doing, I am just, okay, equation numbers are a little bit changed anyway. So now look, dividing equation 2 with equation 1. So what we get, Gh by G will get R square by R plus H whole square. Okay, so this is, you can give a name. Now look, if H is much less than R, that means height is much less than the radius of the earth, then we can just write this G. See, this particular factor we can just expand with binomial theory. Okay, let us just write this part alone. Okay, so let me take this factor R square by R plus H whole square. So this I can write in this way also. See, R square, if I take common, then the numerator and denominator both side R square will be cancelling each other. So it will be like H by R whole to the power minus 2. Now at this condition, the height is much less than R. At this condition, we can expand this like 1 minus 2h by R plus some higher order terms of this h by R whole square. Like this, after that it will come like h by R whole square. This term will come again, then it will come like this. So these higher order terms will come. Okay, but since this h is much less than R, so we can neglect the higher order terms, and we can write this to be nearly equal to 1 minus 2h by R. So this is binomial expansion. Okay, using binomial expansion, we can find out this ratio to be equal to 1 minus 2h by R. Look, then I'll just remove this part maybe. So Gh by G is equal to 1 minus 2h by R. Okay, so this is the thing we got, and see, if we write gh, this will be equal to g into 1 minus 2h by r. Okay, this is another equation. Let us say this is 4. I'll just remove everything. I'll just keep these equations alone. Okay, so maybe I'll write freshly. So what we have got now, g into 1 minus 2 h by r, and the original equation what we had the original equation to be r square by r plus h whole square. Okay, so let us say this is equation 3 and this equation 4. So these are two equations we have got. Look why I have written these two equations. So this is a master equation. When see this is valid, so somewhere actually these are both the variation of acceleration due to gravity with height. Both are expressing the same thing but has different form. Okay, so where to use which one? That is the confusing thing. See, if I if I have r is very nearly equal to h, when my height is nearly equal to h, that time we cannot use this, we have to use this. And when r is much greater than h, we have to use this equation. Okay, I can immediately take one example, that see, if suppose there is a question like this, see there is a question, at what height from the surface of the earth will the value of g will be reduced by 36% of the value at the surface. So in this case, how you can do this? How will you do this? So question, I'll just write the question, at what height from the earth surface, from the surface of the earth, I'm not writing, the value of g, the value of g will become 36 percentage, 36 percentage of g. Okay, of g, 36 percentage of g. G is actually the acceleration due to gravity at the earth surface. So where capital R is given as 6400 kilometer, this is the radius of the earth. So which one of this equation you will be using? Actually in this case, in this particular case, it is better to use the second one, because we don't have the idea of the height first of all, and also the g is 36 percentage of the gravitational acceleration due to earth. So this is 36 percentage, not very less. So so that's why we have to use the master equation or this main equation, equation number 4. So if you use that, look how to solve this problem. Okay, I'll just remove this equation. I'll write again whenever required. Let me solve this problem. We have to use this equation now here. So we have been given that g prime or gh, I'll write gh is equal to 36 percentage of 36 percentage of 36 percentage of G. Actually, it is reduced by 30. So it is the value of G will become 36%. No, actually this not become. This will reduced. G will be reduced by 36 percentage of G. So you have actually here GH is equal to, so it is reduced by 36 percentage. That means G minus G into 36 by 100. So you get 64 into G by 100. Okay. So this much is the value of G over here, GH here. So the question was the gravitational acceleration reduced by 36 percentage of G. Now if you put it here, GH by G, so it implies that GH by G will be 64 by 100. Okay. So this is the left hand side. If we see use this equation, suppose 5, so from 5 and 4, what we can write? We can write 64 by 100 is equal to r square by r plus h whole square. Okay. So in this case, if you first take the root over both sides, you just make square root. So 8 by 10 is equal to r by r plus h. So if you solve from here, you will get the height. So you get 10r, here 8r, so 2, and here 10h, 2r. So you get h is equal to r by 5, r by, sorry, this is 10, and this is 8r. Oh, 8h, sorry, 8. This is 8. 8. So you get h is equal to r by 4. So look what we get here. So h will be r by 4. So this is actually 64004, and then this is kilometer. So you will get 1600 kilometer. So this is not very less. This is actually fourth time. So in this case, actually you cannot use the previous formula what we had. Another situation I can tell you. So we had h is equal to, sorry, gh is equal to 1 minus 2h by r. Okay, and also gh is equal to g into r square by r plus h whole square. So this is the thing we have now, these two equations. So suppose in some cases, if the height is given r by 2, what is the g at r by 2? In that case, if you use the equation, this is suppose 4, sorry, 3, and this is 4, what we got earlier. So if you use this equation, see when h is r by 2, so look, this factor will become 0. So in that case, you will be in trouble. So in this case, so this is actually h is nearly, actually it is comparable to r now. H is actually comparable. So these are two comparable, and or we can say that r is not much greater than h. So in that case, better to use, not better, you have to use this formula. When, so the bottom line is, I have got two formula, 1 minus 2 h by r with height. So this is, I'm just giving 1 because I don't have any equation suppose now, and r square by r plus h whole square. So this equation we have to use when h is much less than r. So this is the condition, and this condition when h is comparable to r. Okay, when this condition comes, you have to use this formula. All right, so we'll go to the next topic: how acceleration due to gravity varies with depth. So in this case also the same assumption will make that this earth is the earth is a sphere, solid sphere. It has radius r, having radius r, and mass capital M. Okay, this is the assumption in this case also. Now the question is at any depth. Depth means what? If you go inside the earth from the surface, if you go inward towards the center, you are going towards the center from the earth's surface, or below the earth's surface at any point below the earth's surface you are going. So what will be like, say, in the mining places, in the place mining places, so those places we'll see how acceleration due to gravity varies when you go below the earth's surface. Okay, so look, I have kept the object of mass small m, suppose, at d depth from the surface of the earth. From the surface of the earth we have kept it d depth. Okay, we know acceleration due to gravity due to gravity at the surface of the earth to be small g is equal to g into m by r square. Okay, this is the one we know. Now we can use this as you have done in case of altitude, or when we calculated gravity with height, that time also use this equation. So in this case you have to remember one thing, that if we write, suppose the acceleration due to gravity is gd, so what we can write, we have to know the distance of that mass small m, or the particular point at this d depth from the surface, at what distance that particular point is situated from the earth's surface, sorry, center of the earth. So that is r minus d. Okay, if the radius of the earth is r and this is d, so this much distance away the object is there. Okay, so we can write this down, like denominator, in place of r we can write easily r minus d whole square. Okay, we can write that r minus d whole square we can write. But what about the mass, whether we can write m itself? This I have already discussed in the beginning. We cannot use this the whole mass of the earth. Now look, the gravitational pull the object will feel due to the earth having radius this much only. Okay, or the inner shell, it will be experience it will be experiencing the gravitational pull due to the portion of the earth having radius r minus d. So this is also a sphere. Now you have to consider this sphere. So that's why I have written this distance r minus d whole square. But what about the mass? Mass also has to be replaced by m prime. You cannot take the whole mass, okay, because the shell of thickness d will not exert gravitational pull on this particular object. So this m prime has to be calculated. If we know the uniform density of the earth is rho, then what we can write? So m prime can be written as 4 by 3 pi r minus d whole cube into rho. So this is what we have to write. So if we just replace this m prime with this factor, then look what we get: 4 by 3 pi, okay, pi, then r minus d whole cube rho divided by r minus d whole square. Okay, what we can do is we can just strike this out, with 1 will be remaining, so I'll just strike it out. So finally what we get, this is the thing we get. Okay, so this is the thing we get. Okay, this factor will be cancelled. All right, so if we write this also in terms of rho, what we can write: g 4 by 4 pi by 3, then r cube rho divided by r square. So if this r square get cancelled with this, so ultimately we get this. Okay, now there are two equations. One is this one, equation 2. This is equation 1. If we divide equation 1 with equation 2, so what we are going to get is, see, I'll write it here. If I take the ratio, this, suppose this is d, gd, the acceleration due to gravity at this d depth from the surface of the earth will be given by, see, if I'm taking the ratio of these two equations, like 1 is to equation 2, then I get, see, this factor is common in both sides, this factor, so I'll just strike them out. Rho is also common because it is a density, uniform density. It is same for the whole mass or whole earth. So you get r minus d over r. Okay. Okay, so then I'll just remove this portion. This whole portion I'll remove. I hope you remember how I have arrived this equation. We have to write the original or real mass of this particular portion of the earth. So we got this r minus d by r. We just simplify a bit, we get this. Okay, so gd, sorry, gd or acceleration due to gravity at any depth below the earth's surface will be varying as this. Okay, so in this case, if you have been given that at depth d is equal to r, that means where you are, depth d is equal to r means where you are. See, depth d is equal to r means what? You are at the center. So what is the acceleration due to gravity at the center? So if d is equal to r, so it will be 1. So you will get gd is equal to 0 at the center. So that's why at the center of the earth, acceleration due to gravity is 0. So weight of a body at the center of the earth will be always 0. Even though the mass of the object is not zero, but the weight at the center of the earth of any object will be zero. Now I can actually there is a numerical problem always. So what I'll do, I'll just clean this portion and let me get a portion for this. So we have got GD is equal to G into 1 minus d by R. And for height, like with height how it varies, there are two equations. I'll write the second one first, 2h by R, and the other one I'll write GH R square by R plus H whole square. Okay, so these are the two equations for height and this equation for depth. Now there is a question, like what is the relation between height and depth? What is the relation between height and depth for the same change in G, for the same change in G? I'll just tell you in other sentence, other word. See, sometimes there will be a numerical problem. They will ask you that if some height is given, suppose some height is given, some 50 meter, 50 kilometer, 50 meter, whatever. If G is having some value G prime at 50 height, same value of same value of G, when do you get or where do you get below the earth surface? Okay, so this question is saying what is the relation between the height and depth for the same change in G? That means if you see in both cases actually G is decreasing. If you go above the earth surface, then also it is decreasing, and when you go inside earth or below the earth surface, then also it is decreasing. So the question is at what depth, like at certain depth, if G is the G prime is the or GD is the value of acceleration due to gravity, so at what height you should go to get the same value of GD? Okay, that is the question. Now look, we know GH is equal to for height. So for this answer, to answer this, we have to write this first, 2h by R. It changes with height. And also look GD how it varies, G into 1 minus d by R. If we equate these two, okay, if we equate these two, then we get the depth, like the relation between the depth and height. Okay, so it will be 1 minus 2h by R is equal to 1 minus d by R. So this 1 getting cancelled, this minus sign goes off, R also goes off. So what you get is d is equal to 2h. That means, see, on the surface of the earth, G is actually 9.8 meter per second square. Okay, if you go d is equal to 2h depth, d is equal to 2h depth, the acceleration due to gravity at height h, whatever you get, you will get the same value of the acceleration due to gravity at 2h depth. So this is the relationship. Hence the acceleration due to gravity at height h above the earth's surface will be same as that of the acceleration due to gravity at d is equal to 2h below the surface. But this fact holds only this case, when this, okay, for this only this case holds or valid when the height is much less than the height height is much less than the radius of the earth. In that case only this particular condition is valid. Okay, so we have learned the variation of acceleration due to gravity with depth and with height, but sometimes there will be a graphical problem in your competitive exam, that what is the variation of acceleration due to gravity, that is g, with distance from the center of the earth. Look, we have got, so that means you have to draw g versus small r curve. Okay, when the r is actually starting from the center of the earth. Okay, so suppose r is varying like this. So at this particular, so on the earth surface, small r is capital R is equal to capital R, and then again at certain point here outside. So how the acceleration due to gravity varies inside, outside, at any point outside. So that variation you have to draw. So look, we'll find out two cases. So one is inside, how it varies outside. So these two things we have to consider. So look, we are taking, first we take outside point. Okay, so take that outside point. That means r is greater than r. Capital R is the radius of the earth. Okay, if your distance is outside the surface of the earth, then how g varies? Okay, look, we know gh is equal to gh by g is equal to r square by r plus h whole square, right? Now if this r plus h has to be, see, this r plus h, that means it is outside point. So if I take this r as r plus h, small r as r plus h, so you look how it varies as r square. So g actually varies outside, it varies as 1 by r square at any point outside. Outside the earth surface. Okay, now we'll take a point inside the earth, or yeah, below the earth surface. Point below earth surface. That means your r is less than small r, a capital R. So in this case, we know the formula, gd is equal to g into r minus d by r. So this is what we know. Now look, this will give you r into 1 minus d by r. So if we just approximately, we can write this varies as 1 by, so this r, let us suppose this r. Okay, so this, okay, let me just repeat this thing. So g we know to be g into r minus d by r. Okay, look, when we go below the earth surface at d depth, Okay, so suppose we are at d depth here, d depth from up surface. So this we can write, this distance we write r minus d, right? So now in this case, actually this is less than r. That means we can write this r minus d to be r, small r by capital R. Okay. Anyway, this is the radius of the earth, so it is constant. This g is the gravitational constant, sorry, acceleration due to gravity on the earth surface. So we can write that gd varies directly proportional to r. Okay, inside the earth. Inside the earth, acceleration due to gravity varies as r. So finally you have to plot it. So I'll just write how it varies. So g varies as 1 by r square. So this is at any point outside the earth surface, and g varies as r any point, at any point r less than capital R. Okay. So these two conditions, g varies like this. Okay. So if we plot this thing, how you plot? See, this is the plot. Look, this is the small r, the distance from the center. So at this particular position, r is equal to 0. So what is the g? As we have learned just few minutes back, that at the center of the earth, the acceleration due to gravity will be 0. So it is 0 over here, and then gradually it increases. So this increases. This part is actually increasing till the surface. It varies as r. That means it is directly proportional to r, as we have learned here. Okay. And see, at this particular position, r is equal to r. This is actually surface. This is the surface point. Small r is equal to r means on the surface. So on the surface, g has a maximum value, and it is written as gm by r square. And if we put all the values, we'll get nearly 9.8 meter per second square. So this is the maximum value which we experience on the surface of the earth. And then as you go above and above the earth surface, it will fall. How it will fall? The acceleration due to gravity g will fall as 1 by height square, or the distance square from the center of the earth. It will fall as the inverse square of the distance you go from the center. So this is the case here. So this is actually inside the earth, inside, and this is outside the earth. Okay. So you will be actually getting a question in competitive exam maybe. So how it varies, how gravitational acceleration varies with the distance from the center. So inside, the acceleration due to gravity varies directly proportional to r. Okay. Acceleration due to gravity will be directly proportional to the distance, and outside the earth it will be inversely proportional to the square of the distance from the center of the earth. Okay. So this is what was the variation of the center acceleration due to gravity with distance, like with we have learned with depth, with height, and in general with distance how it varies. So these are the things we have learned. Now we can, we have another 5 minutes, so we'll learn one more point, that how acceleration due to acceleration due to gravity, or g, varies due to the rotation of, due to rotation of due to rotation due to rotation of the earth. So how it varies? So to understand this, we have to know what is called latitude. Okay, let us learn that part also, how acceleration due to gravity varies at various latitude due to rotation of the earth. So this is the axis of rotation of the earth. Earth also rotates its about its own axis with certain angular velocity, suppose omega. So this is the north pole, this is the south pole, and as you know, this is the east and this is the west. Okay, if you name it. And if you draw a great circle over here, horizontal great circle, which is perpendicular to the axis of rotation of the earth, then this great circle is called the equatorial plane. This plane is called equatorial plane. Okay, look, this plane is called equatorial plane, so which is perpendicular to the axis of rotation. Equatorial plane. Sorry, here equatorial. Just 1 minute. Equatorial plane. Okay. Now look, this you consider this to be the center of the earth. Center of the earth. Now any place on this earth surface, suppose if I take this place, suppose this is a point Q on the earth surface. If we connect this place or this position Q with the center with a line, look, if I just draw a line to connect this Q point, then this line, this line will make an angle with the equatorial plane. Look, this equatorial plane. Equatorial plane is the horizontal plane, okay? And you have a position like this, like this, like this. So these, see, you will get various angle, okay? These angles are called actually latitude. So latitude is generally denoted by lambda, latitude. Okay, this is called latitude. So latitude has 1t. So I'll write the definition of the latitude. Latitude, the latitude of a place is defined as the angle angle which the line of joining the place, line of joining the place to the center of the earth makes, to the center of the earth makes with the equatorial plane. Okay, equatorial plane. So that is called latitude, and that is denoted by lambda. So for this particular case, see the latitude. So if you see the point P, for this particular point P or position P, the latitude is P. See, lambda is the latitude for this particular particular point P. Okay, if you have some object over here, see, acceleration due to gravity will not be same as this place at E. At E, what is the latitude? At E is it is 0. That is the any place which is on the equatorial plane has latitude 0. But what about here? The latitude at any point on the pole, see, this has 90 degree. So at pole it has 90-degree value. At equatorial plane it has latitude has 0 value. Okay. All right. So in this case, I'll just clean everything because I need this figure. Okay. For the rest of the calculation we'll be doing in this figure. So we have learned what is latitude. So that is lambda for this particular position P over here. Okay. Now look what the Earth does. As I was saying, it has a north and south. If you connect this north and south pole with a line, that line will act as the axis of rotation of the Earth. And suppose omega is the angular velocity of the Earth. Okay. And see, we have learned in the rotational mechanics chapter. So all the particles on the Earth surface will actually have the same angular velocity, and they will actually make, all of them will make actually circular motion wherever they are with the common center. Their circles will be like this. Okay, parallel circles, but the center, maybe their radius will be different, but the center will lie on the axis of the rotation. So if I think that there is a particle over here, or there is an object of mass m over here, object of mass m over here at that particular point P. So due to the rotation of the Earth about its own axis of rotation, this particular mass also will be rotating with the Earth with the same angular velocity omega. Okay, with the same angular velocity omega. All right. As the Earth rotates about its axis, the particle also will revolve around that particular axis in a horizontal circle with the same angular velocity. Now, if the particle P is rotating with the same angular velocity omega, and see that particular position has latitude lambda, then look this circle. About this circle, this particular mass is rotating. So if I say the radius, suppose the center C is the center of the small circle about which this particular mass is moving. So Cp, let us say Cp to be small r. Okay. And look, this is the capital R. This is the capital R. And this R is making an angle lambda with this horizontal position, right? Like with this great circle. So I can write this R has two components, one along this way and one along this way. So this small r can be written as r cos of lambda, if you see. So this r has made, so this angle is lambda. So this also will be lambda. If we just draw this CP line to be the small r, so that can be written as r cos lambda. Now look, we know in the circular motion, any object to be, see, earth surface, we are just actually rotating on the earth surface. So anything to be attached to that earth surface, look, first of all, let me tell you, anything rotating in a circular path must be acted upon by centripetal force. So that force is always attracting it towards the center. Okay, so and this is the reason. So centripetal force due to centripetal force, the M is rotating, right, in a circular path, rotating in circular path. That is true. Another point is that we had learnt in the rotational mechanics itself that if the object here M is always continuously pulled by a force, why doesn't it actually fall onto the center, fall onto center? Because so from this fact we can consider that there must be a pseudo force just in the opposite direction, in the opposite direction, which is pulling this particular object away from the center. And this force, centripetal force, and the force, pseudo force, which is pulling away from the center, must be equal in magnitude so that the effect of this centripetal force is cancelled and the object is just rotating in the circle rather than falling onto the center. So this force is called, this pseudo force is called centrifugal force because it is pulling it away from the center. So the force which is pulling towards the center is called centripetal force, and the pseudo force which is exactly equal in magnitude and directing exactly opposite to the center, that force is called centrifugal force. And as we know, these two forces will be equal in magnitude. That's how any object will be rotating in a particular orbit, otherwise it will fall into the center. Okay, so now look, centripetal force. So as we know, centripetal force is m omega square r. So we can write centrifugal force also here as m omega square r. Centrifugal force at this particular position, which is acting away from the away from the center of this center, actually this center, not along this. So it is acting away this way. Okay. Okay. So now look, this one, small r is, you know, small r is what? Capital R cos of lambda. So this is the centrifugal force experienced by the object over here. And look, this centrifugal force is making an angle again. If this is lambda, if this is lambda, if this is lambda, so this also will be lambda. Okay. So then we can take this also lambda. So we can take components of this particular force, centrifugal force, along this way and another along this way. See, m omega square r cos of lambda into sine lambda. Okay, one component along this way. Oh, sorry, this is just, you can see omega square r sine lambda. Okay, omega square small r into, so I'll write sine lambda small r, I'll keep, otherwise it is looking like a big number. So this r can be written as r cos lambda also here. So it will, you will get m omega square r cos lambda sine lambda, this particular force, and this is this one. Look, this force again now at this particular position, the object which is situating, it will be pulled by the acceleration or by the r towards the center. So the acceleration due to gravity will be acting exactly along this way. Maybe I'll just clean this portion little bit so that you can get the view. Okay, look here, the the object situated here at this particular position will be pulled towards the center. And see, this is the mg. It is towards this center. And see, exactly opposite. So this direction, the direction of the weight is exactly opposite to this particular component of the force of this centrifugal force. Okay, so look then, what will be the apparent or the net weight? What will be the net weight of the object at that particular position? That will be, so the of net weight of small m at P will be mg minus m omega square r cos square lambda. Okay, this is the net weight over here. So if I write this is mg prime, because mass is not going to be changed, so what is changing is g. Okay, so we can say that g is changing, so m, so I can just write it here. So g prime will be g into 1 minus omega square r cos square into lambda. So this is the latitude. So you can see this g is varying place to place due to the rotation of the earth. Cos square lambda omega square r cos square lambda. Okay, so lambda, as lambda increases, g also decreases. So when, look, when lambda is 90 degree, that means at the equator, what will be the value of g? So g will be g prime will be g itself. So when it is lambda is equal to 0 degree, so it will be having actually maximum change or reduction. Maximum reduction will be omega square r. So yes, at the pole it will be 0, and at the equator it will have the maximum change in the weight. Okay, so with this I'll stop the class here. So we have learned, due to the rotation of the earth, how gravitational acceleration changes point to point on the earth's surface or at various latitude of the earth's surface. So that is given by this equation: g prime is equal to g into 1 minus omega square r cos square lambda. Okay, all right. So we'll solve few numerical problems in the next class depending on this concept. Gravitational, like variation of gravitational constant, variation of g with distance and due to rotation of the earth also in the next class. So I'll stop it here for today. Thank you very much.